In mathematical physics, we care a lot about whether certain equations in wave equations are stable or not, whether they can create these singularities. There's a famous unsolved problem called the Navier-Stokes regularity problem. So the Navier-Stokes equations that govern the fluid flow for incompressible fluids like water. The question asks, if you start with a smooth velocity field of water, can it ever concentrate so much that like the velocity becomes infinite at some point? That's called a singularity. We don't see that in real life. If you splash around water in the bathtub, it won't explode on you, or have water leaving at the speed of light or anything. But potentially, it is possible. And in fact, in recent years, the consensus has drifted towards the belief that in fact, for certain very special initial configurations of say water, that singularities can form. But people have not yet been able to actually establish this. The Clay Foundation has these 7 Millennium Prize problems, has $1 million prize for solving one of these problems. This is one of them. Of these 7, only one of them has been solved. The Poincare conjecture by Perelman. So the Poincare conjecture is not directly related to the Navier-Stokes problem, but understanding it would help us understand some aspects of things like wave concentration, which would indirectly probably help us understand the Navier-Stokes problem better.
Can you speak to the Navier-Stokes? So the existence and smoothness, like you said, Millennium Prize problem.
Right.
You've made a lot of progress on this one. In 2016, you published a paper, Finite Time Blowup for an Averaged 3-Dimensional Navier-Stokes Equation.
Right.
So we're trying to figure out if this thing usually doesn't blow up.
Right.
But can we say for sure it never blows up?
Right. Yeah. So that is literally the $1 million question. Yeah. So this is what distinguishes mathematicians from pretty much everybody else. Like if something holds 99.99% of the time, that's good enough for most, for most things. But mathematicians are one of the few people who really care about whether 100%, really 100% of all situations are covered by. So most fluid, most of the time, water does not blow up, but could you design a very special initial state that does this?
And maybe we should say that this is a set of equations that govern in the field of fluid dynamics.
Yes.
Trying to understand how fluid behaves, and it's actually turns out to be a really complicated, fluid is extremely complicated thing to try to model.
Yeah, so it has practical importance. So this Clay Prize problem concerns what's called the incompressible Navier-Stokes, which governs things like water. There's something called the compressible Navier-Stokes, which governs things like air. And that's particularly important for weather prediction. Weather prediction, it does a lot of computational fluid dynamics. A lot of it is actually just trying to solve the Navier-Stokes equations as best they can. Also gathering a lot of data so that they can initialize the equation. There's a lot of moving parts. So it's a very important problem practically.
Why is it difficult to prove general things about the set of equations like it not blowing up?
The short answer is Maxwell's demon. So Maxwell's demon is a concept in thermodynamics. Like if you have a box with 2 gases in it, oxygen and nitrogen, and maybe you start with all the oxygen on one side and nitrogen on the other side, but there's no barrier between them, right? Then they will mix, and they should stay mixed, right? There's no reason why they should unmix. But in principle, because of all the collisions between them, there could be some sort of weird conspiracy that like maybe there's a microscopic demon called Maxwell's demon that will, every time an oxygen and nitrogen atom collide, they will bounce off in such a way that the oxygen sort of drifts onto one side and the nitrogen goes to the other. And you could have an extremely improbable configuration emerge, which we never see. And we statistically, it's extremely unlikely. But mathematically, it's possible that this can happen, and we can't rule it out. And this is a situation that shows up a lot in mathematics. A basic example is the digits of pi, 3.14159, and so forth. The digits look like they have no pattern, and we believe they have no pattern. On the long term, you should see as many 1s and 2s and 3s as 4s and 5s and 6s. There should be no preference in the digits of pi to favor, let's say, 7 over 8. But maybe there's some demon in the digits of pi that like every time you compute more digits, it sort of biases one digit to another. And this is a conspiracy that should not happen. There's no reason it should happen, but there's no way to prove it with our current technology. Okay, so getting back to Navier-Stokes, a fluid has a certain amount of energy, and because the fluid is in motion, the energy gets transported around. And water is also viscous. So if the energy is spread out over many different locations, the natural viscosity of the fluid will just damp out the energy, and it will go to zero. And this is what happens in when we actually experiment with water. You splash around, there's some turbulence and waves and so forth, but eventually it settles down, and the lower the amplitude, the smaller the velocity, the more calm it gets. But potentially there is some sort of demon that keeps pushing the energy of the fluid into a smaller and smaller scale. And it will move faster and faster. And at faster speeds, the effective viscosity is relatively less. And so it could happen that it creates some sort of what's called a self-similar blow-up scenario, where the energy of the fluid starts off at some large scale, and then it all sort of transfers its energy into a smaller region of the fluid, which then at a much faster rate moves into an even smaller region, and so forth. And each time it does this, it takes maybe half as long as the previous one, and then you could actually converge to all the energy concentrating in one point in a finite amount of time. And that scenario is called finite time blow up. So in practice, this doesn't happen. So water is what's called turbulent. So it is true that if you have a big eddy of water, it will tend to break up into smaller eddies, but it won't transfer all the energy from one big eddy into one smaller eddy. It will transfer into maybe 3 or 4. And then those ones split up into maybe 3 or 4 small eddies of their own. And so the energy gets dispersed to the point where the viscosity can then keep everything under control. But if it can somehow concentrate all the energy, keep it all together, and do it fast enough that the viscous effects don't have enough time to calm everything down, then this blow-up can occur. So there are papers who had claimed that, you just need to take into account conservation of energy and just carefully use the viscosity, and you can keep everything under control for not just the Navier-Stokes, but for many, many types of equations like this. And so in the past, there have been many attempts to try to obtain what's called global regularity for Navier-Stokes, which is the opposite of finite time blow-up, that velocity stays smooth. And it all failed. There was always some sign error or some subtle mistake, and it couldn't be salvaged. So what I was interested in doing was trying to explain why we were not able to disprove finite time blow-up. I couldn't do it for the actual equations of fluids, which were too complicated. But if I could average the equations of motion of the Navier-Stokes, so basically, if I could turn off certain types of ways in which water interacts and only keep the ones that I want. So in particular, if there's a fluid and it could transfer its energy from a large eddy into this small eddy or this other small eddy, I would turn off the energy channel that would transfer energy to this one and direct it only into this smaller eddy, while still preserving the low concentration of energy.
So you're trying to make it blow up.
Yeah. So I basically engineer a blow up by changing the laws of physics, which is one thing that mathematicians are allowed to do. We can change the equation.
How does that help you get closer to the proof of something?
Right. So it provides what's called an obstruction in mathematics. So what I did was that basically, if I turned off the certain parts of the equation, which usually when you turn off certain interactions, make it less nonlinear, it makes it more regular and less likely to blow up. But I found that by turning off a very well-designed set of interactions, I could force all the energy to blow up in finite time. So what that means is that if you wanted to prove global regularity for Navier-Stokes for the actual equation, you must use some feature of the true equation, which my artificial equation does not satisfy. So it rules out certain approaches. So the thing about math is it's not just about finding, taking a technique that is going to work and applying it, but you need to not take the techniques that don't work. And for the problems that are really hard, often there are dozens of ways that you might think might apply to solve the problem, but it's only after a lot of experience that you realize there's no way that these methods are going to work. So having these counterexamples for nearby problems kind of rules out. It saves you a lot of time because you're not wasting energy on things that you now know cannot possibly ever work.
How deeply connected is it to that specific problem of fluid dynamics, or is it some more general intuition you build up about mathematics?
Right, yeah. So the key phenomenon that my technique exploits is what's called supercriticality. So in partial differential equations, often these equations are like a tug of war between different forces. So in Navier-Stokes, there's the dissipation force coming from viscosity, and it's very well understood. It's linear. It calms things down. If viscosity was all there was, then nothing bad would ever happen. But there's also transport. That energy from in one location of space can get transported because the fluid is in motion to other locations, and that's a nonlinear effect, and that causes all the problems. So there are these two competing terms in the Navier-Stokes equation: the dissipation term and the transport term. If the dissipation term dominates, if it's large, then basically you get regularity, and if the transport term dominates, then we don't know what's going on. It's a very nonlinear situation. It's unpredictable. It's turbulent. So sometimes these forces are in balance at small scales, but not in balance at large scales, or vice versa. So Navier-Stokes is what's called supercritical. So at smaller and smaller scales, the transport terms are much stronger than the viscosity terms. So the viscosity terms are things that calm things down. And so this is why the problem is hard. In 2 dimensions, so the Soviet mathematician Ladyshenskaya, she in the 60s showed in 2 dimensions there was no blow up. And in 2 dimensions, the Navier-Stokes equation is what's called critical. The effect of transport and the effect of viscosity are about the same strength, even at very, very small scales. And we have a lot of technology to handle critical and also subcritical equations and prove regularity. But for supercritical equations, it was not clear what was going on. And I did a lot of work, and then there's been a lot of follow-up showing that for many other types of supercritical equations, you can create all kinds of blow-up examples. Once the nonlinear effects dominate the linear effects at small scales, you can have all kinds of bad things happen. So this is sort of one of the main insights of this line of work, is that supercriticality versus criticality and subcriticality, this makes a big difference. I mean, that's a key qualitative feature that distinguishes some equations from being sort of nice and predictable, and like planetary motion. And I mean, there are certain equations that you can predict for millions of years, and or thousands at least. Again, it's not really a problem, but there's a reason why we can't predict the weather past 2 weeks into the future, because it's a supercritical equation. Lots of really strange things are going on at very fine scales.
So whenever there's some huge source of nonlinearity, that can create a huge problem for predicting what's going to happen.
Yeah. And if the nonlinearity is somehow more and more featured and interesting at small scales. I mean, there's many equations that are nonlinear, but in many equations you can approximate things by the bulk. So, for example, planetary motion, if you wanted to understand the orbit of the moon or Mars or something, you don't really need the microstructure of like the seismology of the moon, or like exactly how the mass is distributed. You just basically, you can almost approximate these planets by point masses. And just the aggregate behavior is important. But if you want to model a fluid, like the weather, you can't just say in Los Angeles the temperature is this, the wind speed is this. For supercritical equations, the fine scale information is really important.
If we can just linger on the Navier-Stokes equations a little bit. So you've suggested, maybe you can describe it, that one of the ways to solve it, or to negatively resolve it, would be to sort of to construct a kind of liquid computer.
Right.
And then show that the halting problem from computation theory has consequences for fluid dynamics. So show it in that way. Can you describe this
right.
idea?
Yeah. So this came out of this work of constructing this average equation that blew up. So one as part of how I had to do this, so there's sort of this naive way to do it. You just keep pushing. Every time you get energy at one scale, you push it immediately to the next scale as fast as possible. This is sort of the naive way to force blow up. It turns out in 5 and higher dimensions this works, but in 3 dimensions there was this funny phenomenon that I discovered, that if you change the laws of physics, you just always keep trying to push the energy into smaller and smaller scales. What happens is that the energy starts getting spread out into many scales at once. So you have energy at one scale, you're pushing it into the next scale, and then as soon as it enters that scale, you also push it to the next scale, but there's still some energy left over from the previous scale. You're trying to do everything at once. And this spreads out the energy too much. And then it turns out that it makes it vulnerable for viscosity to come in and actually just damp out everything. So it turns out this direct approach doesn't actually work. There was a separate paper by some other authors that actually showed this in 3 dimensions. So what I needed was to program a delay. So kind of like airlocks. I needed an equation which would start with a fluid doing something at one scale. It would push its energy into the next scale, but it would stay there until all the energy from the larger scale got transferred, and only after you pushed all the energy in, then you sort of open the next gate, and then you push that in as well. So by doing that, it kind of the energy inches forward scale by scale in such a way that it's always localized at one scale at a time, and then it can resist the effects of viscosity because it's not dispersed. So in order to make that happen, I had to construct a rather complicated nonlinearity, and it was basically like, like it was constructing like an electronic circuit. So I actually thank my wife for this because she was trained as a electrical engineer, and she talked about she had to design circuits and so forth. And if you want a circuit that does a certain thing, like maybe have a light that flashes on and then turns off and then on and then off, you can build it from more primitive components, capacitors and resistors and so forth. And you have to build a diagram, and and these diagrams you can sort of follow it with your eyeballs and say, oh yeah, the current will build up here and then it will stop and then it will do that. So I knew how to build the analog of basic electronic components, like resistors and capacitors and so forth, and I would stack them together in such a way that I would create something that would open one gate, and then there'll be a clock and then once the clock hits a certain threshold, it would close it. It's kind of a Rube Goldberg type machine, but described mathematically. And this ended up working. So what I realized is that if you could pull the same thing off for the actual equations, so if the equations of water supported computation, so like if you can imagine kind of a steampunk, but it's really water punk type of thing where, so modern computers are electronic, they're powered by electrons passing through very tiny wires and interacting with other electrons and so forth. But instead of electrons, you can imagine these pulses of water moving at a certain velocity, and maybe there are two different configurations corresponding to a bit being up or down. Probably if you had two of these moving bodies of water collide, they would come out with some new configuration, which would be something like an AND gate or OR gate. That the output would depend in a very predictable way on the inputs, and like you could chain these together and maybe create a Turing machine, and then you have computers which are made completely out of water. And if you have computers, then maybe you can do robotics, hydraulics and so forth. And so you could create some machine, which is basically a fluid analog of what's called a von Neumann machine. So von Neumann proposed, if you want to colonize Mars, the sheer cost of transporting people and machines to Mars is just ridiculous. But if you could transport one machine to Mars, and this machine had the ability to mine the planet, create some raw materials, smelt them, and build more copies of the same machine, then you could colonize the whole planet over time. So if you could build a fluid machine, which so it's a fluid robot, okay, and what it would do, its purpose in life, it's programmed so that it would create a smaller version of itself in some sort of cold state. It wouldn't start just yet. Once it's ready, the big robot configuration of water would transfer all its energy into the smaller configuration and then power down. Okay, and then like clean itself up, and then what's left is this newer state, which would then turn on and do the same thing but smaller and faster. And then the equation has a certain scaling symmetry. Once you do that, it can just keep iterating. So this, in principle, would create a blow-up for the actual Navier-Stokes, and this is what I managed to accomplish for this average Navier-Stokes. So it provided this sort of roadmap to solve the problem. Now, this is a pipe dream because there are so many things that are missing for this to actually be a reality. So I can't create these basic logic gates. I don't have these special configurations of water. I mean, there's candidates, there's things called vortex rings that might possibly work, but also, analog computing is really nasty compared to digital computing. I mean, because there's always errors. You have to do a lot of error correction along the way. I don't know how to completely power down the big machine so that it doesn't interfere with the running of the smaller machine. But everything in principle can happen. Like, it doesn't contradict any of the laws of physics. So it's sort of evidence that this thing is possible. There are other groups who are now pursuing ways to make Navier-Stokes blow up, which are nowhere near as ridiculously complicated as this. They actually are pursuing much closer to the direct self-similar model, which can it doesn't quite work as is, but there could be some simpler scheme than what I just described to make this work.
There's a real leap of genius here to go from Navier-Stokes to this Turing machine. So it goes from the self-similar blob scenario that you're trying to get the smaller and smaller blob to now having a liquid Turing machine gets smaller and smaller and smaller, and somehow seeing how that could be used to say something about a blow up. I mean, that's a big leap.
So there's precedent. I mean, so the thing about mathematics is that it's really good at spotting connections between what you might think of as completely different problems. But if the mathematical form is the same, you can draw a connection. There's a lot of work previously on what are called cellular automata. The most famous of which is Conway's game of life. There's this infinite discrete grid, and at any given time, the grid is either occupied by a cell or it's empty. And there's a very simple rule that tells you how these cells evolve. So sometimes cells live, and sometimes they die. And there's, when I was a student, it was a very popular screensaver to actually just have these animations go on. And they look very chaotic. In fact, they look a little bit like turbulent flow sometimes. But at some point, people discovered more and more interesting structures within this game of life. So, for example, they discovered this thing called a glider. So a glider is a very tiny configuration of like 4 or 5 cells, which evolves and it just moves at a certain direction. And that's like this vortex rings. So this is an analogy. The game of life is kind of like a discrete equation, and the Navier-Stokes is a continuous equation, but mathematically they have some similar features. So over time, people discovered more and more interesting things that you could build within the game of life. The game of life is a very simple system. It only has like 3 or 4 rules to do it, but you can design all kinds of interesting configurations inside it. There's something called a glider gun that does nothing but spit out gliders one at a time. And then after a lot of effort, people managed to create AND gates and OR gates for gliders. Like there's this massive, ridiculous structure, which if you have a stream of gliders coming in here and a stream of gliders coming in here, then you may produce a stream of gliders coming out. Maybe if both of the streams have gliders, then there'll be an output stream. But if only one of them does, then nothing comes out. Mm-hmm. So they could build something like that. And once you could build these basic gates, then just from software engineering, you can build almost anything. You can build a Turing machine. I mean, it's like an enormous steampunk type things. They look ridiculous. But then people also generated self-replicating objects in the game of life. A massive machine, a polynomial machine, which over a huge period of time, and it always looked like glider guns inside doing these very steampunk calculations, it would create another version of itself, which could replicate.
It's so incredible.
A lot of this was like community crowdsourced by like amateur mathematicians, actually. So I knew about that work, and so that is part of what inspired me to propose the same thing with Navier-Stokes. It is as I said, analog is much worse than digital. Like it's going to be, you can't just directly take the constructions in the game of life and plunk them in. But again, it shows it's possible.